Hello, students. A couple questions here from chapter 3, and it was really more from looks like the review questions. So I'm going to jump there. Let's see here. Chapter 3 review. So a couple pages of these. Let's take a look and see what we end up with. 22 C was the first one. So there's 22A. Let's jump forward. 22B, 22C. Make up a series of instructions such that you will always get back to your original number. Well, these are completely different. But we can kind of talk about the idea of this. It does link back to algebra, and the idea being that you can do things to a number and then later undo them. And if you simplify or use the distributive property, it may not look like what you did originally. So sometimes these are pretty cheesy and people can figure it out. The more complex you make it, the easier it is for people to think there's some magic or math magic going on. And that includes your students. So let's take a look at this one just as an example here. So it's to think of a number. Okay, I'll call my number n. Then add 18. Okay, n plus 18. Then multiply by 4. Got it. So I have 4 times n plus 18. Again, I could leave it like this. And then it says subtract 7. So that would be 4 times n plus 18. I take that whole quantity and I subtract 7. I could do that. I could absolutely do that. But if I then said, it says fill in 2 more steps that will take you back to your original number. So only 2 steps. Notice I could have then afterwards said, okay, add 7, then divide by 4, right? And then subtract 18. And if you look at that, basically what you're doing is you're undoing everything that happened in the previous steps, right? Which again, when you look at it, you're like, well, yeah, you're gonna get back to what you started with, right? So in any case, that's kind of the idea here. What we don't want to do is we don't want to kind of give it away. And so if we're doing something like this with students, it would be great if we could do something, but simplify it so that things look a little bit different. And that's what I would recommend doing here. So the n is okay. So now when I see for this example, this one, 4 times n plus 18, I'm going to write that as 4n plus, and then 4 times 18. Now, again, as I'm doing this, I want you to start practicing more and more doing the mental math. 4 times 10 is 40. 4 times 8 is 32. 40 and 32 is 72. So again, we're kind of mentally thinking about that. I'm not having to do the traditional algorithm. We can get to a place where we can do that a little bit quicker. Next one says take away 7 from that. So now I'm going to take away 7 from that and get myself to 65. So if I want to get back to just my original number, what do I have to do to this number right here? And you could say, well, I have to divide by 4. And yeah, you do have to divide by 4. But if you divide by 4, we have to use the fact that the dividing by 4 would be for the entire quantity. And 65 is not divisible by 4, so now we've got decimals or fractions coming in. So instead, what I'd recommend is saying, oh, here's the next step. I could just add 65. And now notice none of these pieces up here look like a 65 or anything close to a 65. So that would seem fairly strange to a person. But if you do take this quantity and you add 65, notice you had subtracted 65, you add 65, you now end up at the 4n value. And then I would say divide by 4. And so I would just divide by 4 and you get back to your original number. You could try this with any number that you're thinking of as long as you do these pieces. So the idea of part C is simply to make your own and then make up a series of instructions that you will always get back to your original number. Now, if you really want to make this entertaining for students or a little bit more like, what? That kind of stuff, bring in a couple of components that are a little strange. So, for example, we know that 91 is 7 times 13, right? So if you look at something like this, you could say, okay, I want you to multiply your number by 7 after you add 6 or something along those lines, right? So you now have 7n plus 6. You distribute, now you have 7n plus 42. Then you say, okay, now take that number, multiply by 13. And you're like, what? So you multiply by 13. Now you have 91n plus 13 times 42. Again, if I want to practice doing this multiplication, 10 times 42 would be 420. 3 times 42, why don't I do 3 times 40, which is 120, and 3 times 2, which is 6. So I get 546. Okay. So now I'm sitting here with this number. And again, I might say, now I want you to subtract I don't know, 500 and actually, you know what I would do? I'd probably subtract enough so that when I divide by 91, I could say then divide by 91, and I'd end up with like n plus 11. Oh my gosh, that'd be so cool. Because then no matter what number they tell you, right? Or n plus 9, maybe something like that, right? So you can think of that number as being plus 10 minus 1. And then if you want an n plus 9 at the end, then I need 91 times 9. So, okay, 91 times 9, 91 times, just 90 times 9 would be 810 plus another 9. So 819. Wait, 81 and a 9. Yeah, okay, so that works. Yeah. Because 9 times 9 is 81. Those are the 10s, and 9 times 1 is 9. So what I need is 819 plus 546. And so if I take away the 546, it gives me a 3. 7, 2, so I get 273. So then I'd say, okay, now add 273, and somebody does that, and they get this number down here, which is what, 819. And then I tell them, okay, now divide your number by 91 in a calculator. And someone's furiously doing this, but you already know before they start that it's just whatever their number is plus 9. Okay, so if you want to get to their number, what you do is you have to go backwards. So you could say, I'm going to take away 10 from their number. So let's just say their number was the number 23, right? At this stage, you wouldn't have the number 23. You'd have the number 32 because you have n plus 9. And so what you do is you just say, okay, I'm going to take away 10, which gives me 22, and then you add 1, and you'll always be able to get back to their number. So that's the idea, is to kind of show the power of both algebra, the distributive properties, and the fact that if you use the distributive property, even if you take 5 or 6 steps to get somewhere, you can undo it in 2 steps with addition, subtraction, or multiplication and division. So pretty cool question right there that you can use to impress your students. All right, let's see here. 37. 37. So let's take a look at 37. It says, estimate the following addition using front end with adjustment and rounding. Okay. And 38 is using clustering. So these are different addition techniques. Let's see here. So let's see here. What was the question? Why did they round 0, 8 to 0 in the front end estimation with adjustment step? So the front end estimation is just estimating the front end. So all you're doing is really taking that front piece, like 500, 300, 200. These are front end because it literally is the front end of the number. And then you do an adjustment afterwards to make it a little bit easier. The difference between this and rounding is rounding, if you say you want to round to the nearest 100, then you would just have 500. 398 would be 400. 255 would be 300. 408 would be 400. And 998 would be 1,000. And then you would add those numbers up. So I'm rounding and then adding. So that's the rounding portion. So the front end, when I do this, then I would say, okay, now I want to add something on. So for the 500, I would probably add a 40. For the 398, I'd probably add 100 as my adjustment. For 55, that's a tough one. If I want to be as accurate as possible, the last number right here rounded down, this one rounded up in a sense, my adjustment was up. My next adjustment's going to be up. This one's going to be up. So I might even push this one down and say I'm going to adjust by 50. Then this one I would adjust with a 10. That's a 400 with a 10. and this is a 900, and I'd add another 100 on there for my adjustments. So that's how I would do front end with adjustments. Then I'd sum these pieces up. To be honest, for a list that long, it might actually be quicker. Like if you just wanted a quick estimate, rounding is probably your quickest estimate. Yeah, so you just got to be kind of careful. Rounding, even though people love rounding, it does create some issues. For example, if you had 250 plus 350 plus 450 plus, I'll also put another plus in there, plus 550, right? So if you think about this, when you round to the nearest 100, the most that you could be off by is 50. And so this technique, when you round to the nearest 100, this would be 300, 400, 500, and 600. And if you actually add the numbers together, you get 5 plus 3 plus 2 is 1,000. So 1,400 plus another 200 is 1,600 is the actual. But over here, I get 1,800. But each number, the max they would be off is by 50 if I'm rounding. That's like the worst case scenario. And because of rounding, you actually hit the worst case scenario quite often. So there are other techniques with rounding that make things a little bit easier. So for example, like you might take 250 and instead of rounding it, you look at it and it's like halfway between what 200 and 300. Like it's like right in the middle. So it really doesn't matter which way you round it. You're off by 50 each time. And so one way to get around that is to around that, enjoy my pun there, is to actually move to whichever one of these is even. So if I see a 200, that's even compared to 300, which is not. So I would round here. So no, it seems a little strange, but 250 would round to 200. 350 would round to 400 because that's the closer of the 400 and 300. 4 is the even one. 450 would round to 400 and 550 to 600. So I'd only have even numbers here. And that would give me a sum of 1,600 that would balance it out pretty nicely. So there are other rounding techniques. This book isn't showing you all of those, which, isn't bad, but just be aware that there is more than that. And again, for the exam, I would simply be asking you to estimate something, not necessarily saying estimate with front end estimation with adjustment. I think that's a little bit cumbersome. Let's see here. What comes next? Next is 39. Okay, so let's take a look at 39. All right. Yeah, these are fantastic. This is kind of what I was just saying. I mean, you want to use the distributive property to make your life easier. And with multiplication especially, you want to do it. So let's see, you're computing just the following. Yeah, so when you have something like this, try to combine. It's basically algebra, but with numbers. So for example, if you had a problem that said 75x plus 20x, right? You would probably look at that and say, oh, these are like terms. So why don't I just combine those and write 95 x's? And it may not seem like much to you, but this is the identical problem to saying 75 times 37 plus 20 times 37, because that's really what's happening here. And so when you multiply these together, you could just combine them and say it's really 95 times 37 because because all you're doing is combining like objects. When you're in algebra, all you have is these x's. Now that you have a number, don't think of it as anything different. If the number is exactly the same, then the mathematical principle is exactly the same. And you've turned two multiplications plus an addition into one single multiplication, which has got to be a little bit easier. So if we come up here, and so I'll do one for example. I don't know if I need to do all of them. Not sure which parts. Let me check the email again really quick. What did it say for parts? Let's see here. It doesn't really. Does it? Okay, let's clear the drawings here. Okay. Why is it they add 1 to the number being multiplied when they can take away the number being added? Yeah. Okay. So I think it's just understanding that distributive property perhaps might be where the question's coming in. So let's do, maybe one or two of these just to kind of show. Maybe I'll do one at the top, and then I'll do kind of one more at the bottom just to kind of show why the distributive property is so powerful. So again, if I had 999 x's and I added one more x on there, could you rewrite this so it's a little bit easier and neater? And the answer is sure. 999 x's plus one more x is 1,000 x's. So now if you had 999 groups of 47 and I added one more group of 47, the distributive property says I could rewrite this as 47 times 999 plus 1, which, if you look at it, is exactly what you would do with the values over here. You end up with 1,000 times your number. And I got to tell you, that's a whole lot quicker. 1,000 times a number is very quick compared to doing 999 times 47. And then when you get done, adding 47 on to that. So it's just a way of making sure we can do things that are really nice, quick, and simple. The next problem, I see a 43 here. I see a 43 here. That's great. So that means I have 43 factored out, multiplied by what looks like 59 plus 41. And these are completely compatible numbers because 5 and 4 is 90. 9 and 1 is 10. That gives you 100. So this is just 100 times 43, which is 4,300. And I will absolutely be faster doing that than actually doing the multiplication and then adding things up. Similar with the subtraction parts that you see down there. Those subtraction pieces aren't meant to be. You have 1,003 of something, you take away 3 of the same thing, you have 1,000 of them remaining. So very similar pieces. And I think the only two, like down here at the bottom, these, when you look at it, they're intended to use that property. So when you see 101 times 35, instead of coming over here and doing some traditional mathematics, rewrite it as 100 plus 1 groups of 35, and then use the distributive property. Because 35 times 100 is quick, and 35 times 1 is quick. And then you just have to add those together instead of going through an entire process. And 98 times 35 seems like kind of a crazy one, but think 98 is very close to 100. Why don't we think of 98 as 100 minus 2 multiplied by 35? So again, 35 times 100 is meant to be quick, and 35 times 2 is also pretty quick because you just double it, gives you 70, and you end up with 1,000, and you take away 70. So that's how you can do these problems very, very, very quickly. Okay. So that's 39, 41. Let's take a look at 41. Scroll down. Oops, got to get to the next page. 41, prove that this is closed under addition. All right. So it doesn't matter what the number is. So I'll do a slightly different number, but that really won't make a difference. So here we go. Let's prove that this is closed under addition. Closed under addition means what? If I add 2 objects in the set, I will get another object in the set. So I'm going to prove that my set, I'll call it D, and I'll do multiples of 7, where n is a whole number. Okay. So if you need to, you can write out some of these numbers. You could say, okay, what do I have? I have plug in 0 for n, that gives me 0. Plug in 1 for n, that gives me 7. Plug in 2 for n, 14, 21, 28, 35, and so on. So I have a really powerful tool here now. This is a arithmetic sequence. What I want to say is that if I take any 2 objects in here, I'm going to add them. They would give me another object in the set. So as an example, if I grab these 2, 14 plus 21 gives you 35. And guess what? 35 is in the set. But that's just an example. And an example doesn't prove anything. So if we want to prove something, what we want to do is we want to start with 2 things that are in the set. So assume that A and B are in your set. This is the set I called D. Okay, well, that means that A has to equal 7 times something. You could use N. You don't want to use it more than once, so you could use N if you wanted to. I'm going to choose different letters for this. I'm going to use J and K, I guess. So A is equal to 7J, where J is an element of the whole numbers. Okay. And B would be equal to 7 times k, where k is an element of the whole numbers. And again, that's the definition of the set. Okay. I want to prove it's closed under addition. So what I want to do now is let's take a look at, I'll say, consider a plus b. Now my goal is, I really hope that a plus b looks like one of these things. So I'm going to say a plus b, and what does it equal? It equals 7j plus 7k. Using the distributive property becomes 7 times k plus j. And take a look here. J plus k is a whole number. Remember, j was a whole number, k was a whole number. So j plus k is a whole number. Why? Because whole numbers closed under addition. My set, maybe, maybe not, but the whole numbers, we definitely know those are closed under addition. So if it's closed under addition, then this object, j plus k, is just a whole number. And I showed this to one person in class that seemed to kind of click. In your definition, I know it looks like an n, but realize that n is just holding the place for any object. So you really need it to be 7 times something, and that something just has to be a whole number. Well, you just proved that j plus k is a whole number, and you now have 7 times j plus k. So what I can conclude is, since that's what a plus b is equal to, that means a plus b is an element of your set D. Why? Because everything in set D looks like 7 times some whole number, and you just proved that. So we picked two things to start with, we added them together, we showed that the sum has to be in our set. Therefore, D is closed under addition. And I can put a nice little check mark there to show that we've done it. All right, there we go. Love it, love it, love it, love it. Let's see here what else. And 42. Let's see here in 42. Whew. Let's see here. If one of the 83 members, the president, makes the first phone call and starts the clock, each person is assigned, each person's responsibility after the call is to call 2 other assigned members until all members have been called. Okay. So, so we start with one person who makes a call, right? And that takes 30 seconds. Okay, boom, we're here. Now that person has to call somebody else. Each person's responsibility after receiving calls is call 2 other assigned members until all members have been called. Okay, but each call takes 30 seconds. All right. So now after the end of this, right, they have called one person. So now 2 people know. So now each one of those people has to call more people, right? Okay, so let's see here. They call 2 more people. And 30 seconds later, 4 people know, right? So I got to think about this. So person number 1 is the PTA president. And the PTA president makes the first phone call. So the PTA president calls here and calls here. So the PTA president has now called 2 people. Each member is supposed to call 2 assigned members until all members are done. Okay. So that means they're done calling. Okay. So right now at this point, 4 people know. Because if you think about it, the president called one person and then called another person, right? Oh, actually, this would only be 3 people now, right? No, they called one person. That person called one additional person, and that took 30 seconds. So now president calls. So actually 3 people know at this point. President called this person. Oh, president had to call someone else. There we go. But they don't make that call right up here. Yeah, the first call, if we look at time-wise, right? President, person number 1, person number 2, if we want to call him that, right? President makes one phone call to here. This person is the one who received that call. So this person makes a call. and the president makes a call. So at the end of 30 seconds, right, the president knows, person number one knows, and because president called person number one. Yep. So then over here, this person called person number two, let's just say with one of their calls, then that person knows and they begin calling from there. So if we can create a sequence here, we can figure out how long it's going to take, the least amount of time necessary to reach all 83 members of the group. Okay, so I definitely want to make a pattern for this. And if I can make a pattern, it's gonna be great. So I'm gonna need a little bit more space than I gave myself initially. Okay. So here we go. Let me get a little bit more white space. Where's my white space piece? Okay. Well, actually, you know what? I'm just gonna share a new screen. We'll just share a whiteboard. Okay, here we go. Now I got the whole screen. All right, so let's see here. So president knows, president calls one person, right? So I think what I want to do is I want to make a little tree here because the president still knows. So the president ends up here still knowing. So after 30 seconds, the president knows, and that's the blue one. And then the red dot is the actual call that was made. Okay, there we go. So now this person, they are going to continue knowing, but they have to call someone. Okay. And the president's going to call someone as well, but the president will continue knowing. Okay. So yeah, so after one phone call, so this is 30 seconds, then we can kind of think of this as kind of dash line. There's 30 seconds. Here's the next 30 seconds. So we're 1 minute in and we've got 4 people that know. Now, if we go through and solve this problem as if everybody keeps calling one additional member every 30 seconds, and then that person's supposed to continue calling, it's going to look a little different. But let's try this. So now president has now called 2 people, right? So the president is done because the president had 2 people coming off of there. So now this new person, they continue knowing, but they also have to call another person, right? And this is the person that was their first phone call. So this becomes their second phone call. And there's their second phone call. This person up here continues to know, but they also have to make a phone call. Okay. Now I'm going to change the color here because the president continues to know and exist, but didn't make any more phone calls. So let's see how many we have now at this stage. So president calls, that's 1 call from here. President calls, that's 2 calls from here. Okay, so 1, 2, 3, 4, 5, 6. I have 7 now. Okay, I have 7 after 90 seconds. Okay, so now let's take a look and see what happens next. Okay, so the president, so I'll put a line here. President continues knowing. There's 1. See if we can make a pattern out of this. This person that the president called who is standing right here, that person continues on down to here. So they continue knowing. They have to make 1 more phone call. So now this person has called 2 people. That is great for them. Next person up, they continue knowing and they make their first phone call here. This person, let's see here. So the person, this will be the first person who got called. They have now made 2 phone calls, so they will continue on just like the president did. And then this person just continues knowing, but has to make a phone call. And up here, this person right here continues knowing, and they have to make a phone call. And this person above them continues knowing, and then they have to make a phone call. All right. Phew. Let's take a look. So right at the beginning, at 0 time, we had 1 person who knew. After 30 seconds, we have 2 people who know. After 60 seconds, 1, 2, 3, 4 people know. After 90 seconds, 1, 2, 3, 4, 5, 6, 7 people know. Okay. And now after another 30 seconds, so we're at 2-minute mark now. So it doesn't look like we're going to get there very quickly. It looks like it's going to take a while, but I think it's going to blow up pretty quickly on us from here. So let's see if we can get there. Okay, so now let's see here. So anybody who has 2 dark blue lines is going to turn light blue. Okay, 2 dark blue lines, that's how that would continue. Let's see here. Anybody who is just starting, they will have 1, but let's check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I have 12 now. I have 12 people who know after 2 minutes. Next up, okay, so I'm going to go to my light blues. So my light blues continue. Anytime I have 2 dark blues in a row, it turns light blue. Anything that was light blue continues. Anything that's 2 dark blues in a row continues. Anybody who wasn't, they have to continue making phone calls, right? So let's see here. So this person has to make a phone call, and they called a new person, and they still know. This person still knows, has to make a phone call. Be a lot easier if they just kept calling and calling and calling until it got to the end. I mean, I want to be perfectly honest. This person knows, but they have to make a new phone call. So every red line is a new phone call that gets made, a new person. Let's see here down here. So this person right here, who just got informed, they have to call someone, but again, they continue to know. This person continues to know, but they also have to call someone new. It's their second call. Down here, makes a call, but they each still continue knowing. Doop, 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 doop. I wonder what's so top secret about this. Maybe they could just post the information somewhere. But again, it's a good question, right? It's a good question to think about. Maybe. Let's see, here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So now I'm at 20. Okay. So what you might begin to see is a really nice pattern forming. And I'm going to illustrate it here for you. So what I can see is I end up with this number, okay, 1 plus 2, right, in a sense, because I'm adding one additional piece in the end. 1 plus 2 is 3, and I'm comparing it to 4. 2 plus 4 is 6, and I'm comparing it to 7. 4 plus 7 is 11, I'm comparing it to 12. 7 plus 12 is 19, I'm comparing it to 20. So when you look at it, you get this really nice pattern that the 2 numbers before your number, if you add them together, you need to add 1 to continue on. That's one approach. Yeah, I think the other approach is going to be a little bit more complicated because you're really doubling until you get to a place where you start subtracting doublings as well. So for example, when I get to the stage with 4, to get to the next stage, I would double it, but then I would subtract 1 because there's one person who is not making the phone calls anymore. Then I would double again, but I'd remove 2. 2 is the term from back here because I had 2 people who now are at that stage. Okay. And then double again would be 12 times 2 would be 24 because everybody makes 2 phone calls. But then you have to say, but wait a minute, who made phone calls before? There were 4 people. So you'd say 2 times 12 gives you 24, but you have to take off the 4 that already made phone calls. So there's 2 approaches you could take with this problem. One is more what's called recursive, and the other which is called direct. So whichever way you choose to do it. So let's see here. Every time if I did this pattern, I'd go 1, then 2, then 4, then 7. We got 12, then 20. So you can see, even me, I'm going to write it out just to make sure I'm on the right track. But every time you think about it, by the time I go back and say, well, who's made 2 phone calls in the next phase, right? In the next phase, it looks like it's going to be 7 people who were here who by that point in time definitely will have made their 2 phone calls. So there'd be 1 person here, 2 here. This person is not, they haven't made 2. This person's made 2. So there's 3, not 2. There's 4. There's 2 from there. There's 5, not from there. There's 6, not from there, but there's 7. So I get 7 people who have made 2 phone calls. Everybody else has to make a phone call, which means it's themselves plus one other person. And so you end up with this really nice strategy. I could double this number, which looks like it'll give me 40, but I have to remember that 7 people 2 phone calls ago would have made their last phone call. So this right here would actually be 33. If you wanted to check and say, what about that other pattern you showed, Scott? Well, that's fine. You could take these two numbers, add them together, gives you 32, and then you plus 1, and it gets you there. Just like I would here, if I add these, I get 6 plus 1 more gets me to 7. So that's the same pattern, and we could keep going. So we need to know, when does this actually end? So I would double again. That would give me 66. Looks great, except I have to take off 12, which gives me 54, because I take off 12. Then I double again, which is 108, but this time I have to take off 20, which gets me to 88. And 88 would be perfect because there's only 83 people in this group. And now we would just count the steps. So let's see here. One person knows and starts making phone calls. Here goes the clock. That's 30 seconds. There's another 30 seconds. That's 1 minute. Okay, I'll count the second minute would go 30 seconds and 30 seconds. That's 2 minutes. Let's see here, 30 seconds and 30 seconds. That's 3 minutes. And finally, 30 seconds and 30 seconds. So I could actually be done with everything in 4 minutes using this type of phone tree. Would it be quicker if everybody just kept calling? Like why would you stop after just calling 2 people, right? Maybe you have a list and you keep calling till you get down everybody on your list. Would it be quicker? So 1, then 2, right? Then 4. So if this person kept calling, then this wouldn't be 7. I would have 1 more on there, then it would be 8. Right? And so basically, since every person is calling 1 additional person, you would actually get a perfect geometric sequence of 1, 2, 4, 8, 16, right? Think about it as we keep going, because everybody would have kept calling. 32, 64, and lastly would be 128. So if you count these steps, and you'd say 30 seconds once, every 2 is 1 minute. There's 1 minute. There's 2 minutes. There's 3 minutes. So yeah, if you did it the other way, you could do it in 3.5 minutes instead of waiting 4 minutes. So, but again, I think they were just trying to push us into something that's a little bit more detailed. All right. So this would be one of those recursive sequences that you kind of get to, and then you want to make sure you're subtracting the pieces from before. That's why we don't want to count people who've already made their 2 phone calls. And it does, it links back to the numbers we had already. So if you knew a person was starting here, once you move forward 2 steps, they're done with their calls. From that point on, I need to make sure I subtract them out. So I would have had 4 times 2, should have been 8. But again, this person's done. So even though they still know, I don't have to worry about them making another phone call. So I have to remove 1 from that. And that's why 4 times 2 minus 1 gets you to 7. All right. That was kind of cool. Let me make sure I answered all the questions in that, and there it is. Phew. All right, that should do it for now. If you have other questions, let me know. Otherwise, have a great night. Off you go.